Hey, welcome to part 3 of thermochemistry. Hopefully you enjoyed part 1 and part 2. Part 3 is going to be legendary. This is Mr. Ayton, and we're going to be taking a look again at another way, a third and final way, to find the enthalpy of a reaction. If you remember back in part 1, to find the enthalpy of the reaction, we took the sums of all the products of our enthalpies of formation minus the sum of all my reactants of my enthalpies of formation. And in part 2, we took a look at Hess's law when we've been given a list of reactions. And we also took a look a little bit at the stoichiometry as well. And so in part 3, we're going to be taking a look at bond energies, yet another way to find the enthalpy of a reaction. And this is when we've been given a list of bond energies. That's what we're going to do, a bond energy problem. Okay? The first thing we want to make sure we understand about bond energies is it is positive energy to break bonds. Okay, if you're going to break anything, a piece of wood, if you're going to split a piece of paper in half, you have to put energy into it. And so it's positive endothermic energy to break bonds. To form bonds, say on my product side, it's going to be negative energy. We're going to release energy when we form bonds. It's going to give off energy. Okay, and if you remember back to our intermolecular forces chapter, when I made the question or the statement, are you breaking bonds when we are boiling something? And you guys all said, no, we are breaking the attractions, the hydrogen bonding or the London dispersion forces, the attraction between the molecules. You're not actually breaking bonds. Here in Thermo right now, guess what we're doing? We're breaking bonds and we're forming bonds. But this is a chemical reaction here is what we're doing. Okay, and so what we want to do at the end is make sure you add up all your energies, just like in Hess's law, to get the enthalpy of the reaction. And a really good point to keep in mind with these types of problems that helps me out is I like to draw out all my molecules. Man, it helps me out big time in order to do that. Okay, let me give you an example of a bond energy type of problem, and we know it's a bond energy type problem because what do you know? They gave us a list of bond energies. Okay, if they give you a list of a table here of bond energies, guess what? You're not doing products minus reactants. You're not doing Hess's law. You're doing bond stinking energies. Okay, and so what we want to do is, like I said, draw out our molecules. You can take a look on the reactant side here. I have 2 hydrogen gases. I draw both of those. I have 1 oxygen gas, 1 double bond there. Okay. If you take a look at the product side, I have 2 waters, and I'm actually going to draw that out, those 2 waters. The reason I draw this out is, you see that 2 in front of the water, the coefficient of 2? You might have a tendency to say you're only going to form 2 bonds. But if you take a look, how many bonds are we actually forming here? 4 bonds. 4 individual bonds. So what are we going to do? Let's take a look. We are going to multiply 436 by 2. Why? Because we're going to break both of these hydrogen to hydrogen single bonds. How many oxygen double bonds are we going to break? Oxygen to oxygen double bonds? We're going to break 1. So again, that's positive energy. You're putting in that energy to break those bonds. And on your product side, we're going to multiply 4 because we're actually going to form 4 OH bonds. Okay? And it'll be negative because it will release heat when we form those bonds. And so what are we going to do? We're going to multiply all of our numbers, make sure we get all of our values. And if you see, I put the reactant side as red and the product side as blue, which means the red is going to be positive endothermic, the blue is going to be negative exothermic. And what are we going to do at the end is add up all of these energies, and what do you know? We get negative 481 kilojoules per mole, and this reaction is exothermic. It gives off negative 481 kilojoules for every 1 mole in this reaction. Okay, this is your Thermo Part 3 question. I've given you a list of bond energies, and you are going to, for me, you are going to find out, calculate the enthalpy of the reaction based on the information in the above table for that reaction, for the combustion of methane. And B says, if the delta S, if the entropy is 186 joules per mole Kelvin, keep in mind that joules, okay? Make sure you might want to change that bad boy at 290 Kelvin. Then I want you to calculate the delta G value for this reaction that you use in part A. Also determine whether this reaction is spontaneous or non-spontaneous. And again, when you're done that part 3 question, what are you going to do? You're going to come to MrAyton.com, you're going to go to the contact page, and you are going to send me an email with your answers. And I will email you back if you're right or if you're wrong. If you got to go back to the drawing board, or if you are done your winter break, Christmas break assignment. I hope you had a great Christmas break, and I can't wait to see you guys back on that whatever day we come back from break, and have a great second semester there. All right, this is Mr. Ayton signing off. See you guys.